Okay, to be able to derive the equations of motion for a multi-body system, one of the first things we need to be able to do is to compute the kinetic energy and the potential energy of different systems that are connected together. Okay, so let's review how to compute the kinetic energy, first of all, for a particle. So let's suppose that we have a particle of mass m, and that particle is moving with some speed. Let's say if there's a position, or we have some speed v, then the kinetic energy for that particle is equal to 1/2 mv squared. Now, this would be translational velocity if in fact v is a vector. So if, for example, our particle of mass has a length, or is moving in velocity with the velocity vector v, where, for example, v would be v in the x direction, v in the y direction, v in the z direction, if we were to express this vector v in a local coordinate system. Then for this case, the kinetic energy, K, is equal to 1/2 m, and now we're going to have V transpose V, where, in other words, that's equal to, that's equal to 1/2 m Vx squared plus Vy squared plus Vz squared. Okay, now if I have two particles of mass, so for example, if I have a particle of mass m1 moving with some velocity v1, and another particle of mass m2 moving with velocity v2, then the total kinetic energy of the system is going to be K is equal to 1/2. We're just going to sum the kinetic energy of the first mass, m1 v1 transpose v1, plus the kinetic energy of the second, 1/2 m2 v2 transpose v2. And this extends to a whole system of particles. So if we have many different particles, let's say, all with different mass m sub I and velocity v sub I, then the total kinetic energy, K, is going to be equal to 1/2 times the sum over all particles I, mi, vi transpose vi. Now, this starts to become interesting if particles are connected together. So, for example, if we have a particle of mass m1 and it's connected by, let's say, a massless rod to another particle m2, and this rod, let's say, has a length of L, and let's suppose that the entire, so to make it easy at the beginning, let's say that the if we connect some point here, that this entire rod is moving with some velocity v, then that implies that m1 also moves at velocity v, and also m2 moves at velocity v. Therefore, the total kinetic energy, K, is going to be 1/2. Total kinetic energy will be K is equal to 1/2. And now we'll have both m1 moving at v, but also m2 m2 moving at velocity v, and that means that the total kinetic energy can be expressed as m1 plus m2 v transpose v. Now, let's suppose that this rod not only is moving at velocity, well, instead of moving at velocity v, let's let it spin. So in this case, again, we have a rod and mass 1, mass 2, and if we pick some point on this rod, and let's suppose that this rod is spinning with some angular velocity vector v. Okay, so v could be a three-dimensional vector, again, that would be expressed as omega x, omega y, omega z in an xyz coordinate frame. Okay, then what is the velocity of each? So let's suppose that the entire rod is not translated in any way. What is the velocity of each of those masses? So from physics, you may remember that the velocity is equal to, the velocity is equal to the angular velocity cross with the position vector, let's say Ri, Vi. So if we have, in this case, from the center out, this would be R2, and from the center this direction, that would be R1. Therefore, the kinetic energy, the total kinetic energy, is going to be 1/2 mass 1 times V1 transpose V1 plus 1/2 m2 V2 transpose V2, and that's equal to 1/2 m1. And now if we substitute in from this expression, we have omega cross R1 transpose omega cross R1 plus 1/2 m2 omega cross R2 transpose omega cross R2. Now, this expression is a little bit ugly, and so we want to simplify this a bit. And so we're going to use two trig identities. So the first trig identity that we're going to use is, so this is just from or I guess not trig identity, but these are from the cross product identities. So these are identities that you probably saw in calculus, and these are the two identities. We have A cross B cross C is equal to B times A transpose C minus C times A transpose B, and also A transpose B cross C is equal to B transpose C cross A, and it's also equal to C transpose A cross B. So if we look at, let's just look at the expression omega cross R transpose omega cross R. And the first thing we're going to do is apply this particular identity, where this whole vector will be A, and then omega will be B, and R will be C. So from this expression then we can say that this is equal to omega transpose C, which is R, cross A, which is omega cross R. Okay, and then we're going to use this identity to write this as omega transpose, and then we'll have so in this case R is A, omega is B, and R is C. So from this expression up here we have omega times A transpose C minus C times A transpose B. Okay, now what we'd like to do is get omega on the inside and the outside of this expression. So we're going to rearrange things a little bit here. This is omega transpose, and then since this quantity is a 1 by 1 scalar, and remember omega is a vector, 3 by 1, and over here we have a 3 by 1 scalar, and again a 1 by 1 scalar. So we can move scalars to either side of vectors, so we can write this expression. Let's just pull the omega to the other side of the first expression, so we'll have R transpose R times omega minus, and then let's just rearrange the parentheses here, R times R transpose, and we'll put the parentheses here times omega. Note now that in fact this is still a 1 by 1, 3 by 1. This thing is now a 3 by 3 matrix and a 3 by 1. So if we want to pull omega to the right, so we want to write this as omega transpose an expression and then omega over here on the right, the first quantity we'll have to put a scalar times identity, R transpose R times identity, so that we multiply each element of omega equally, minus and then R transpose. And just to refresh your memory, if you know R transpose is equal to Rx, Ry, Rz, and then R transpose would be Rx, Ry, Rz. Times the center of mass plus 1/2 omega transpose J omega. Okay, and this is the expression for any rigid body, meaning it's not squishing or flimsy or whatever. Any rigid body, if we can find the center of mass and the velocity of the center of mass, and then the angular velocity, omega, and it's actually you can think of it as spinning about the center of mass. It's actually the same quantity whether it's, in other words, omega isn't tied to a particular position. So spinning about the center of mass versus spinning about an axis turn out to be, you have the same angular velocity, but possibly a different J. So we will, because R would be different. So we will assume that J is computed about the, so J is always computed about the center of mass. Okay, and that is the way you compute the kinetic energy for a rigid body system.